our world and beyond, space, in partnership with the European Space Agency.
For billions of years, our galaxy, like countless others, existed in pitch blackness.
Black is not only important in the universe, it is dominating. It is really the key component of the universe, and that's what makes it so fascinating in the end.
Everything together is 100%, then 75%, 3/4, is the dark energy. And then about 21% is dark matter. And black holes, they are even less. So what we see in the universe, if you look at the stars, is only about 0.5% of the total energy density of the universe. That's why we say there's this big dark side.
It's a mystery, we don't know it. And the word dark in that sense does in fact explain our ignorance.
Black holes, dark matter and dark energy hail from the dark side of the universe. Dark because so little is known, but also because there's literally no light. 3 European specialists illuminate the issue just ahead of 2009, the UNESCO-designated Year of Astronomy.
2009 is the Year of Astronomy, and we want to teach the public during this year and inform them about this dark side of the universe, which represents some of the deepest and most interesting puzzles of modern physics.
Stars die or explode and transform into supernovas, giving birth to black holes. The hows and whys of the process have long fascinated scientists and inspired numerous science fiction writers.
A black hole is a very concentrated mass. So if you just take matter, any kind of matter, us for instance, and compress it to a small volume, then of course the gravity becomes very strong. This would be a situation where we would actually turn the Earth into a black hole. And then in fact light could not escape from the inside of this sphere to the outside, so you would have a black hole.
Our dark story doesn't end there. Dark matter, which was unheard of until the 1930s, is next on the list. Observation of dark matter is not easy, but scientists know it's present and that it plays a vital role.
Dark matter is matter which pulls on the rest of the other matter, just like normal matter, gravitation, but it doesn't emit any light. So you cannot see it with ordinary instruments, but you can see its effects on the gravitation of objects around it. Suppose that you were to look at a dance floor in a dark hall, and you have ladies in white, and you have all the men in black. And you don't see the men because it's dark. And you see those ladies dancing around something, and you don't know what it is because you can't see it.
The dark energy is a very deep mystery, perhaps the deepest mystery in physics at all that exists at the moment.
It's a mystery which science is trying to solve. There are already some explanations.
After the Big Bang, the universe expanded greatly, and the gravity of all the materials slowed down the expansion of the universe. But then 5 billion years ago, very suddenly, the universe started accelerating again its expansion. And we think that this is caused by this dark energy field, and it makes the universe expand.
But if these phenomena can't be seen, how can they be detected?
This dark side of the universe is not directly visible, but we still see its effects. We feel, for example, the gravitational forces. That's how astronomers detect it. That's how we study it. And we can also simulate it on computers and make it shine there.
This huge hall in the Max Planck Institute in Germany is at the heart of the Virgo project. An ambitious international scheme, it aims to map out the universe in images using powerful computers.
in our own galaxy, the Milky Way galaxy, we have analyzed where the chances for finding the dark matter, where they are largest. And we found that it's best to use the satellite, the Fermi satellite, to look close to the center of the galaxy.
In this search for signs of the invisible, there are satellites at work, but that's not all. On the other side of the world, in the Atacama Desert in Chile, is the Very Large Telescope.
What we set out to do is to take the nearest object where we suspected a black hole might reside, and that's the center of our Milky Way, and make measurements there with ever better technology, bigger telescopes, new techniques, new detectors over those 20 years, where we were then able to measure the motions of material stars around where we suspected there might be a black hole.
In cooperation with NASA, the European Space Agency is also investigating black holes using the Hubble telescope. By looking at residue left by the Big Bang and with missions such as Gaia, scientists hope to further their understanding of the evolution of the universe.
And then with missions like Gaia, which will allow us to study in detail our universe today, or missions like XMM, Newton, the X-ray telescope, which can allow us to study black holes today in our galaxy. And finally, we will have, perhaps, if it's approved, a mission like Euclid in 10 years from now, which will allow us to study dark energy in its present-day configuration.
It's difficult to imagine something you can't see or an energy you can't feel. However, astronomers believe these abstract concepts are the glue that binds our universe together. But it's a universe which is not standing still.
There was a period in the early universe where there was no light, in a sense. There were no stars. The universe was dark. We call this the Dark Ages. Eventually, the first star formed, the first galaxy, and there was light, if you like. Now we have billions of stars in each galaxy, and there are billions of galaxies. Now, in the far future, the dark energy field will make the universe so big that we can't see any external galaxy anymore. Then the night sky will fall black in that sense again. So the future of the universe looks again dark, if you like.
Waiting for the return of absolute darkness, the seen and the unseen continue their strange dance, although the steps remain a mystery.